The title of this talk is Means, 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 and in this talk we will discuss three means or averages of two positive numbers, and these three means are the arithmetic mean, the geometric mean, and the arithmetic-geometric mean, and the relations of these means with a certain calculation done by the mathematician Gauss in connection with the length of the lemniscate. And this lemniscate is a specific type of curve in the plane which has this shape of the infinity symbol or the number 8 lying on its side. So we'll give a precise description of this lemniscate later on, and we'll also see what the connection of these means is with this length of the lemniscate. So that's what this talk is about. So let's first start by introducing the three means. So if a and b are two positive real numbers, and we'll always assume that a is less than or equal to b, then by a mean or an average of these two numbers, we mean any of the numbers which lies in between a and b. So this blue portion over here, when a and b are depicted on the number line. And but there are some means or averages which appear quite frequently, and so we give them special names. So the first of these is the arithmetic mean, and this we will denote by capital A of A and B, and that by definition is A plus B by 2. So this is what we usually mean by an average of two numbers. So for example, the arithmetic mean of 1 and 5 is 1 plus 5 by 2, which is 6 by 2, which is equal to 3. So if A and B are depicted on the number line, then the number corresponding to this arithmetic mean is exactly the one corresponding to the midpoint of the line segment with A and B as the endpoints. So this is the arithmetic mean, but there are other means too. So here is what we mean by the geometric mean, and this we will denote by capital G of A comma B, and that by definition is the square root of the product of the two numbers. But why do we call it the geometric mean? What's geometric about it? Well, it arises in certain geometric situations. So here are two instances. So first, let's consider the problem of squaring the rectangle. So imagine that we have a rectangle with side lengths A and B. So the area of this rectangle is AB. And suppose that we want to construct a square which has the same area as this rectangle. Well, if the side length of the square is x, then the area of the square will be x square, and this x square has to be equal to ab, so x has to be equal to square root of ab. So we see that the geometric mean arises as the side length of the relevant square, which equalizes, whose area is equal to the area of the given rectangle. Here is one more instance where the geometric mean arises, and this can be thought of as the construction of the geometric mean given two line segments of lengths A and B. So suppose we have two line segments, one of length A and the other of length B. Then we can draw a circle with this line segment as the diameter. So then the diameter of this circle will have length A plus B, and so the radius of this circle will be A plus B by 2, which is the arithmetic mean. But also the geometric mean arises in this situation. So where the first line segment of length A ends, we can erect a perpendicular to the diameter, and this perpendicular will at some point intersect the semicircle, and it will create a line segment, and the length of this line segment turns out to be the geometric mean of the two numbers A and B. So let's see why this is true. So essentially this relies on the fact that if we take any point on a semicircle, then it subtends a 90-degree angle with respect to the diameter. And one can use this fact to show that this height is then the geometric mean of A and B. So let's see why this is true. When we erect a perpendicular to the diameter, we create two right angle triangles, and I claim that these two right angle triangles have the same shape. So this is because if this angle is theta, then this angle is 90 minus theta, because this angle is 90 degrees, And since this whole angle is 90 degrees, it follows that this angle will be 90 minus this angle, and hence it's equal to theta. And so if we reproduce these two triangles over here, we notice that they have the same shape because this theta corresponds to this theta, and this angle is 90 degrees in both ones, and this angle is equal to this. So since these two triangles have the same shape, the ratio of the corresponding sides has to be the same. So this gives us that a by x is the same as x by b, where this height is x. And by rearranging, we get x square is ab, so that x is equal to square root of ab. So indeed, this height is the geometric mean. So this actually also gives a visual proof of what is called the arithmetic geometric mean inequality, which says that the geometric mean of two numbers is always less than or equal to the arithmetic mean of those two numbers. And this we can see immediately because we know that in the semicircle, the largest height which is perpendicular to the diameter will of course be the radius, and that is the arithmetic mean. Meanwhile, the geometric mean will be somewhere else, and so necessarily its height, this length will be smaller, and so we get that the geometric mean is less than or equal to the arithmetic mean. So this is a visual proof of this arithmetic geometric mean inequality. Okay, so far we have seen what's the arithmetic mean, what's the geometric mean, but what is the arithmetic geometric mean? So this is constructed as follows. So suppose that we have been given the two numbers a and b, we will construct the arithmetic geometric mean through an algorithm like this. So we first take the arithmetic mean of these two numbers, and that corresponds to this midpoint of this line segment, and that we call as the number b1. And we take the geometric mean of these two numbers, and that we call as a1. So of course a1 will lie to the left of b1 because we know that the geometric mean is less than or equal to the arithmetic mean. So starting from the two numbers a and b, we have now got these two new numbers, a1 and b1, where a1 is the geometric mean of the previous numbers and b1 is the arithmetic mean of the previous two numbers. But we can continue this process. So we again take the arithmetic mean of these two new numbers, and that I call as b2, and we take the geometric mean of these two numbers, and that I call as a2, and again a2 lies to the left of b2. And we can keep doing this process, creating a sequence of geometric means a1, a2, a3 and so on, and a sequence of arithmetic means b1, b2, b3 and so on. And visually it's clear that these two numbers are getting closer to each other, and in fact both the sequence seem to be convergent with a common limit. And this common limit is what we call the arithmetic geometric mean. So the fact that the two sequences are convergent is clear because the sequence of the geometric means is increasing, but it's bounded by b, it can't go beyond b, so it has to converge to something. So let's call it alpha. And similarly, the sequence of arithmetic means is decreasing, but it can't go beyond a, and so that sequence also has to converge, say to beta. And finally, the fact that the two limits alpha and beta have to be equal follows from this recurrence relation, because for large n's, this beta bn plus 1 starts looking more and more like beta. Meanwhile, an for large n starts looking more and more like alpha, and this bn starts looking more and more like beta. So passing the limit as n tends to infinity, we get the equation that beta is equal to alpha plus beta by 2, or 2 beta is alpha plus beta, and hence alpha is equal to beta. So the two sequences, one of the geometric means and the other of the arithmetic means, does have a common limit, and this common limit is what we call the arithmetic geometric mean of the two numbers, and that will denote by ag, a comma b. Also, these two sequences converge very rapidly, which is clear visually. The a and b suddenly jump to a1, b1, which then come ever closer together, a2, b2, and this process will converge very fast. And to give a example, suppose we start with a being the number 1 and b being root 2. So I have truncated, of course, the infinite decimal expansion of root 2 to some 22 decimal places over here. And let's carry out this algorithm. So we first take the arithmetic mean of these two, which I have written over here, and the geometric mean of these two, which I've written over here, and then we continue the process. So again, arithmetic mean of these two, which appears over here, geometric mean of these two, which appears over here. And already we see that the first 4 decimal places are exactly the same, 1981 here, 1981 here. But let's continue. So again we take the arithmetic mean, and again we take the geometric mean written over here, and again arithmetic mean of these two written over here, and geometric mean of these two written over here. And we notice that already in 4 steps there is convergence to some 19 decimal places. You have 1981, 4023, 4735, 5922, 074, and exactly the same thing appearing over here. And only after the 19th decimal place you have some different numbers appearing here. So these two sequences do converge very rapidly. What's remarkable is that one would expect that these computations have been done on a modern day computer, but actually they already appear from this 1800 paper of Gauss, and he did these calculations by hand. So it's quite remarkable that he could do computations to 19 decimal places without the use of computer. Okay, so far we have seen the arithmetic mean, the geometric mean, and the arithmetic-geometric mean. But what does this have to do with the length of the lemniscate? So first of all, what is the lemniscate? Before we discuss that, let's consider the case of the ellipse. So the ellipse is a familiar planar curve, and one description of the ellipse is like this. You have 2 points A and B in the plane, which are called the foci of the ellipse, and we have a fixed length. And the ellipse is then created as the locus of a movable point P, which maintains the sum of the distances to A and B as being a constant, the constant being the length we start off with. So if we imagine 2 nails over here and a string of the given length, which we have stretched out with the help of our pencil point, so this is where our pencil point is, and if we keep stretching out the string and move our pencil, so then that will maintain a constant sum to P to A and B, because the length of the string is not going to change. And in this manner, when we trace out this curve, that will be an ellipse. And we know that the ellipse is a common object. For example, the planets move around the sun in elliptical orbits with the sun at one of the foci. So that's what an ellipse is, and a lemniscate is a similar object where rather than maintaining that the sum of the distances is a constant, we now have that the product of the distances to the 2 focal points A and B is a constant. So the locus of all the points such that PA times PB is constant describes such a curve, which is called the lemniscate. And this is of course one description, but here is sort of a standard lemniscate which can be described in polar coordinates like this. So here is the origin, and if we have a point P, then we measure the angle that this ray makes with the positive real axis, and let the distance of this point P to the origin be denoted by r theta. Then the set of the P's on this lemniscate is precisely the set of all r thetas and thetas which satisfy this equation. R theta square is equal to cos 2 theta. So for example, when theta is equal to 0, then this cos 2 theta will be 1, and so the corresponding r will be 1. So when you are over here, when theta is 0, your distance is equal to 1. But as the theta increases, the cos will decrease, and so the distance to the origin will decrease in this manner. And at theta is equal to pi by 4, this cos 2 theta will become cos of pi by 2, which is equal to 0, so the distance becomes 0. But one has to be careful with this equation, because since you have a non-negative number over here, only those thetas are allowed for which cos 2 theta is non-negative. And so not all real thetas appear, but only those thetas which render cos 2 theta as non-negative. And then you can check for yourself that for those allowable thetas, you get these this lemniscate curve. So that's the lemniscate, and it's a natural question to ask for this standard lemniscate, what is the length arc length of this lemniscate. And just like in calculus, one can express the area under the graph of the curve described by the graph of a function in terms of an integral. One can also describe the length of this lemniscate with this parameterization in terms of an integral, and it turns out that this integral boils down to this particular integral. It is 2 times integral minus infinity to infinity dx divided by square root of x square plus 1 times x square plus 2. Of course, this is a very complicated integral, and it turns out that unfortunately this is not expressible in terms of, the indefinite integral is not expressible in terms of elementary functions with, with the trigonometric functions, the exponential and logarithm function, the algebraic functions, and so on. And what makes it sort of hard is that you have two different numbers appearing over here. You have a 1 which is not equal to 2, but instead of 1 and 2, suppose you had a positive number like a square. So if this was x square plus a square and this was also x square plus a square, then the integrand would be 1 by x square plus a square, and that function does have a primitive. So it's the derivative of something. And then we can calculate this integral by using the fundamental theorem of calculus. So we'll see that 1 by x square plus a square does have a primitive. Essentially, it's the arctan function, and we'll see that in a minute. And that would have been an easy integral, but unfortunately you have different numbers over here, and that makes this hard. Nevertheless, Gauss, the German mathematician who lived in the 18th to 19th century, he managed to do something with this integral and express this integral somehow using these numbers 1 and 2. So we'll see that soon enough, but let's first see what would have happened if this integrand would be somewhat simpler. What's the arctan or tan inverse function? Well, suppose you have a right angle triangle where this base length is fixed as 1 and this height is thought of as a variable. So if we have a certain height x, then the angle that we get correspondingly will be called tan inverse of x. And we are interested in finding out what is the derivative of tan inverse of x. In other words, we are interested in this difference quotient, the limit as dx tends to 0 of tan inverse x plus dx minus tan inverse x divided by dx. So rather than giving we will show that this derivative is in fact 1 by 1 plus x square, but rather than giving an analytic proof of this, let's give a geometric argument to convince ourselves that this should be true. So we start with a right angle triangle where this height is x and this base length is 1, so that we know that this red wedge angle is equal to tan inverse of x. And then by Pythagoras theorem in this right angle triangle, this blue hypotenuse length will be the square root of 1 square plus x square. So that's this hypotenuse. Now suppose I increase the height by a tiny little amount dx. So then in this big triangle, big right angle triangle, this big wedge angle will be tan inverse of x plus dx. And so this little wedge angle will be tan inverse x plus dx minus tan inverse x. But that's the numerator over here in this difference quotient, and so we are making progress. So now with this as center, this point as center, and this blue line as radius, we draw a little arc, a little circular arc, and that's this green segment over here. In this process, we have created a tiny triangle, and we claim that this is like a right angle triangle. This is almost like a right angle triangle. And why is this? Because first of all, we notice that this side length, this light blue side length, and this side length is the same because they are both the radius of the circular arc. And so this is an isosceles triangle. And since this little wedge angle is tiny, because this dx was very small, it follows that both of these equal angles are almost 90 degrees. So that means that this triangle is almost a right angle triangle over here. Moreover, we claim that this right angle triangle has the same shape as this big right angle triangle. And why is this? It's because, well, since this is this red wedge angle, if we call it as alpha, then this angle will be 90 minus alpha. And since this angle is 90 degrees, it follows that this will be 90 minus this angle, which was 90 minus alpha. And so this is the same as alpha. So this little angle is exactly the same as this red wedge angle. So this right angle triangle is similar to this right angle triangle. It has the same shape. And so the ratio of the side to hypotenuse in the little triangle should be the same as the side by hypotenuse in this big triangle. So let's see what is the side by hypotenuse in this little triangle, where the side that I'm interested in is this green side. Well, this green side was this circular arc, more or less. And since this little wedge angle is this thing, and this length, the radius, is square root of 1 plus x square, it turns out that this one will be the angle multiplied by the radius, which is this quantity over here. So this is the angle and this is the radius. Meanwhile, what's the hypotenuse in this little right angle triangle? Well, that's dx, so that I've written over here. So side by hypotenuse in the little triangle is this thing. But what's side by hypotenuse in the big triangle, which has the same shape? Well, the green side is 1 and the hypotenuse is square root of 1 plus x square. But now we see that this was the difference quotient that we were interested in, and if I take this square root of 1 plus x square down over here, we get exactly 1 plus x square. So indeed this difference quotient starts looking like 1 divided by 1 plus x square, and that this hopefully convinces us that the derivative of tan inverse of x is 1 by 1 plus x square. And using this fact, we can also, with the chain rule, conclude that the derivative of this function is 1 by x square plus a square, where a is a positive constant. So now we have got that this function does have a primitive, and it's essentially the tan inverse function, modulo some constants. So since this function has a primitive, we can calculate its integral. So let's first look at this integral. Integral from minus infinity to infinity dx divided by x square plus a square, and we claim that this is pi by a. Well, why is this so? Well, first of all, this is an even function, so its graph is symmetric about the y-axis. So if we want to calculate the total area, it's enough to just calculate the area from 0 to infinity and then take twice of that, because if you imagine folding the paper along this line, we'll just get twice the area. So it is just 2 times integral 0 to infinity dx divided by x square plus a square. But we know that this function has a primitive. That's what we just saw, and it's this function. So if we substitute it over there, then we have that this integrand is just the derivative of this function. But since we have the integral of a derivative, by the fundamental theorem of calculus, it's just the function evaluated at one endpoint minus the value of the function at the other endpoint. But what's tan inverse of infinity? Well, if the x goes off to infinity, this angle opens up to pi by 2. So tan inverse infinity is pi by 2. On the other hand, what happens when the x shrinks to 0? Well, then this angle collapses to 0. And so this tan inverse of 0 is 0. And so we see that it's this. The 2 cancels with this one, and so you get pi by a. Excellent. So we have got this integral, and recall that the reason we were interested in this integral is because it's a simpler version of this more complicated integral where the a and the b are different. Well, what happens if the a and b are the same? Then the integrand becomes this one, and that's our integral that we have just calculated. So we know that this integral is pi by a, and so if I replace throughout a by b, we also get that this integral is pi by b. But the real integral that we are interested in, which is related to the length of the lemniscate, is this integral, where the a was 1 and the b was root 2. Well, what can we say about that? Well, all we know is that this integrand, of course, lies in between this integrand and this integrand. So the integral that we are expecting lies in between this integral and this integral. In other words, the integral that we are expecting lies in between these two numbers. So if we write it as pi by something, that something has got to be in between a and b. So it's a mean. But which mean? Well, Gauss proved that in fact this integral is pi divided by the arithmetic-geometric mean of a and b. And how did he prove this? Well, let's see a sketch of his proof. So first of all, he called this integral as I of a comma b. He just gave it a name. And of course, it depends on a and b. For example, when a is 1 and b is root 2, you get some number. If a is 18 and b is 1,036,036, then you get a different number. And so it depends on the a and b. So he called this I of a comma b. And then he made a change of variable. So with this substitution, t is equal to x minus ab by x, he concluded that this integral is the same as what effect is produced is that the limits don't change, but the a is now replaced by the geometric mean of a and b, and the b is replaced by the arithmetic mean of a and b. And so we notice that this integral is has the same form as this integral, except the a has been replaced by the geometric mean and the b has been replaced by the arithmetic mean. So what's the effect of this step? Well, if we start with the two numbers a and b, and you have a certain integral corresponding to those, it doesn't matter if instead of the a and b, you take the geometric mean of a and b and the arithmetic mean of a and b. So you can in some sense replace these two numbers by their geometric mean and the arithmetic mean. But we can continue this process. So instead of these two numbers, we can replace them yet again by their arithmetic mean and the geometric mean, and we can continue this process, and the integral does not change. So the I of AB is the same as I of A1 B1, is the same as I of A2 B2, is the same as I of A3 B3, and so on. Where recall that this A1, A2, A3 were the sequence of geometric means that we had created before, and B1, B2, B3, and so on were the sequence of arithmetic means that we had created earlier. But we know that for large n's, they start looking more and more like the same number, the arithmetic geometric mean. So what's essentially happening is that since this is a constant sequence, it coincides with the limit of this constant sequence. So this is the same as the limit as n tends to infinity of I of a n bn. But for large n's, a n and bn both start looking like the arithmetic geometric mean. So this is the same as the integral of the same number, the arithmetic geometric mean of the old numbers and the arithmetic geometric mean of the old numbers. But what happens when the a and b become equal? Well, then we get our previous integral, namely x square plus whatever number we have square. And that integral, we know, whenever you have the integral of x square plus square, then you get pi by And so in our case, when you have x square plus the arithmetic geometric mean square, you get pi by the arithmetic geometric mean. And in this manner, he showed that this integral is the same as pi divided by the arithmetic geometric mean. And using this fact, then he could calculate the length of the lemniscate as 2 pi divided by the arithmetic geometric mean of 1 and root 2. And it's unclear when he did this exactly, but from his diary entries, one can fathom that this was clearly when he was less than the age of 22 years. And some claim that in fact he was as young as 14 years when he discovered this. So that's the end of this lecture.